In this video, I'm going to discuss power series. Now, a power series is a series with a variable x that's raised to some power n. So basically, it has a dummy variable x that's raised to some power n. There are two types of power series. You can find a power series that's centered at the origin, okay? Or you can find a power series that's centered at C. The difference is the ones that centered at the origin, there's nothing added to x. For example, if you look at the first example here, you just have a sub 0 plus f sub 0 x plus a sub 0 sub 2 x squared. So you don't have anything added to x. If you look at this example here, it gives you an idea of what I'm talking about. So this is an alternating series, and it's centered at the origin because there's nothing that's added to x. And the second one here, you have another series which is centered at this one is centered at -2. All right, so C is 2, which means it's centered at -2. So this one here is centered at -2. Okay, so that's the difference between those two types of series. Now, here is an example of a power series, and I just want to use this to discuss the details about certain features of a power series. Now, this is a power series. We can actually generate the first three terms of this power series. So this will be equal to, if you plug in 0, you just end up with 1. X to the power 0 is 1. And then if you plug in 1, you'll have x plus x squared, and so on and so forth. All right? So this goes to infinity. Now, if you inspect this series, you can notice that the first term is 1. So A is 1. And the common ratio is x. It's actually a geometric series. All right? This is simply a geometric series where the first term is 1 and the common ratio is x. The common ratio is a variable, as you can see. Yeah, it's x. Now we know that a geometric series converges when x, the common ratio, is between -1 and 1. All right. So this series will converge. So this series converges when its common ratio, which is x, is between -1 and 1. Now, I just want to talk a little bit about the sum of this series. Now, the sum of this series, we know that it's a geometric series with common ratio x. So sum to infinity of a geometric series. So sum to infinity of this series will be, we know it's a over 1 minus r, which means we are going to end up with our a is 1 over 1 minus x. So which means that, you know, this power series converges to a function. All right? But it converges to this function when x is between -1 and 1. So basically we are saying that this power series, which is given by this, will be equal to f of x, which is given by 1 over 1 minus x, um, when x is between -1 and 1. Now, this is a very important conclusion, all right? So, which means that we can actually represent power series as functions, all right? We can represent power series and functions, and we can check this idea if it makes sense. Remember, x can take any value between -1 and 1. Um, so suppose x is equal to something like a half, yeah? Suppose x is equals to a half, then we know that the sum of this series will be given by, remember x is a half, so in place of x I plug in a half uh, to power n, which will give us, when you plug in 0, you'll have 1 plus a half plus a quarter, and this is a geometric series with common ratio a half, which means that this series will converge to 1 over 1 minus a half, which will be equal to 1 over a half, which will be equal to 2. All right? So this series will converge to 2. And we can check that by using the function. Remember, we have two representations here. All right? We have the series, which is given by that. We have the series, and we have the function as well, which is given by this. So we can check using these two different representations if this is true, especially when x is equals to a half. So f of a half will be equal to 1 over 1 minus a half, which also will be equal to 1 over a half, which will be equal to 2. And you can see that these two answers are the same, all right? So, which means that you can actually represent a geometric series. You can represent a power series as a function for a given number of values of x. So that's very important, and we'll discuss this later on when we look at other examples. All right, I'll carry on to some examples that will give us more insight on this idea. And now we use the ratio test to determine the convergence of a power series. So if you have a question asking you to, determine the convergence, the interval of convergence of a power series, you can always use the ratio test to check that. Now, example 1. For what values of x does this series converge? Now, we know that from ratio test, the series converges if all right. So if the limit of the absolute value of s sub n plus 1 over s sub n is less than 1, then the series converges. And we can use that to find what you're being asked here, the values of x where this series converges. So back to ratio test. We know that s sub n is equal to x minus 3 over x minus 3 to power n over n, and s sub n plus 1 is equal to x minus 3 to power n plus 1 over n plus 1. And then we can carry on to find the limit. So the limit as n approaches infinity of x minus 3 . Okay. Um, this can be written as x minus 3 to power n plus 1 over n plus 1 multiplied by n over x minus 3 to power n. We can go ahead and simplify that as well. Um, so we can rearrange this around. So I just want to put these guys together so that we can be able to simplify using indices. Um, x minus 3 to power n plus 1 divided by x minus 3 to power n. That will simplify to just x minus 3. So that will be x minus 3 multiplied by n over n plus 1. Now we can factor out x minus 3. Remember, we are finding the limit as n approaches infinity. X is just a dummy variable here. We can, take it out. So we'll have x minus 3. Remember, it's an absolute sign of the limit. All right. At this stage here, you can use LHS, L'Hopital's rule, LHR, sorry. So what you'll end up with is if you find the limit of n over n plus 1 using LHR, L'Hopital's rule, that will be equal to 1. So we'll just end up with absolute value of x minus 3. But we know that for convergence, this should be equal to, this should be less than 1. So converges if no, this converges if, and you can write this inequality as negative 1 x minus 3 1, and then we write it as just add 3 on both sides. We'll end up with 2 and 4. Now we have to check the endpoints. All right. So to check the endpoints, we can just work it out. For example, at x is equals to 2, our series, just plug in 2 in place of x. So if you plug in 2 in place of x in this series, right, you'll end up with negative 1. So this will be now this series is an alternating series which converges by alternating series test. Okay, now we'll check the second point. So our series will be plug 4 in place of x, and then you'll end up with that. Well, because if you plug 4 in place of x, you'll end up with 4 minus 3, which is 1. So our series is a harmonic series, which you know that it diverges by p-series tests. So this diverges. So what's our final conclusion? Our final conclusion is that the interval of convergence includes 2 but does not include 4. So hence, okay.